Later in the semester, you are going to hate this problem because you'll be given a force at E, not the angle, and you're going to have to use statically indeterminate methods in order to solve for how much each of these stretch. But for today, we're just learning strain, so the 2-degree rotation is given. And so this is really just a geometry trigonometry problem to understand the concept of strain. And fundamentally, strain is a unitless parameter, change in length divided by original length. So if we have original and final length, boom, that's it. That is strain. And the trick to solving strain problems is to make a good drawing. You need your original drawing and a final drawing after everything has moved and stretched a little bit. This final drawing will help give you the triangles or lengths that you need to find. So I start off drawing my original triangle, ABH, in order to find the new length for the wire all the way on the left-hand side. And then with orange, I kind of draw this little small triangle up above it to show what happens when AB rotates upwards a little bit. Now, technically, this 200 millimeter orange line is the length of the diagonal. It's the hypotenuse. So AH is technically not vertical anymore once it has rotated a little bit. However, we are going to assume that it does stay vertical, and I'm going to prove to you that that's okay to do. But for simplicity, because it's going to make the problem a little bit easier, we are going to make a small angle approximation that AH remains vertical and stretches straight upwards. So why are we allowed to do that? Well, it's because sine and tangent are basically the same for very small angles, right? If we use sine of 2 degrees, this is the proper, correct way to find this little change in H. H would be 6.98 millimeters. But what we haven't accounted for is that there's also a little tiny horizontal change as well, which is minuscule. Now, if we use tangent of 2 degrees, which is technically not correct, this is where we keep the 200 as the horizontal distance, we get 6.98 millimeters. So the difference is in the thousandths place, and we don't even have that much precision in our numbers for this problem. So this shows that, yes, we are justified in making this assumption that tangent and sine are the same and that our lines remain vertical. So easy game, change in length over 200. We're using the 6.984, the one we got from tangent, assuming that it stays horizontal and vertical, 0.0349. I'm calling the units millimeters per millimeter because the numerator is millimeters and the denominator is millimeters. Now, you could call this unitless if you want. The millimeters and the millimeters, they cancel out. However, I have a mental block against boxing a final answer at the end of my problem without units in it. Whenever I draw a box, if I have not boxed units, that sets off triggers in my brain like, you messed up. So, millimeters per millimeter is also a regular normal unit for strain. Even though it can cancel, you are allowed to keep, distance over distance, like inches per inch. And I recommend that you should do this because it will help to remind you that you didn't just forget to include the units. So you are intentionally including them. And it also potentially makes sure you haven't made any unit mistakes. And now my second cable, where I've got a distance of 300 and 300, and I'm connecting the cable as one side and the pivot point of the rigid bar, right? That's the sort of the bottom left side here. And then my orange line shows what happens after it rotates downwards a little bit, that 2-degree angle. Now, using tangent then, we get a change in height of about 10 millimeters, which gives us the same strain, 0.0349. And this, again, should kind of raise a flag in your brain like, wait a second, should these have been the same? I got the same answer for 2 different cables. And in this case, yes, because both of my triangles were perfect, like 45-degree angles, like 200, 200, and 300, 300. So the ratios of how much leverage arm the rigid bar had to the length of the cable, it was the same ratio. So that resulted in the same amount of strain. I am going to get a different value of strain though for the third cable because now I have a much longer leverage arm, 500 millimeter leverage arm to the pinpoint versus a 300 millimeter cable. So the 2-degree rotation now causes about 17 millimeters of stretch. So change in length in the numerator, right? L final minus L initial divided by original length in the denominator, the 300 millimeters, get about 0.05 millimeters per millimeter for this cable. There's a link to my full mechanics materials playlist down in the description. Don't have to watch all the videos right now, but just bookmark it so you can come back to it all semester whenever you get to each new topic. Good luck on your next test.